Can I begin? So, today I want to explain some applications of what we did in quite generality last time, namely the central limit theorem in a quantum context. So I decided to begin from the absolutely simplest and most elementary of such theorems, because in this way you will be able to see, first of all, how the general theory is applied. Second, the basic differences that arise from between classical and quantum probability. Third, the fact that sometimes, in some cases, we can directly compute not only the existence of the limit distribution, but a much richer structure. So let me begin. So the simplest central limit theorem is the Moivre-Laplace theorem, which has to do with the Bernoulli process. As you remember, my second lecture, Bernoulli process is the process in which the probability space has only 2 points, the classical probability space has only 2 points, and the analog of this classical probability space is what nowadays is called the qubit, but is essentially this is the analog of the Bernoulli process. So let us consider, I want to introduce some very famous operators which are called the Pauli matrices, which were introduced for the notion of spin. For this reason, in physics, the Bernoulli process is also called the spin 1/2 process. I prefer the more neutral term Bernoulli, because exactly the same formalism is not only for spin, but also for polarization. There are several quantum observables which are dealt with the same space, which is always this. So we have these two operators that we will see in many features. These four operators form a linear basis of the 2x2 matrices, and they satisfy some commutation relation, which I have written here for your commodity. But the crucial things to be remembered and that will be used in the following is that this is a nilpotent operator. Sigma plus, remember, is a triangular. Sigma plus is upper triangular, and sigma minus is a lower triangular. And you will see in a moment the interpretation, the physical interpretation, why they are called in physics the rising and lowering operator. And plus and minus are orthogonal projection. So the important point is sigma plus is nilpotent. Therefore, also sigma minus is nilpotent. And the modulus square of sigma minus is a projection. So they are both partial isometries also. And the same for sigma minus. Okay, these are simple exercises you can do. The interesting point, you remember, with the Bernoulli process was let us, in order to introduce I will not speak of the Q deformation today. I only stick to the simplest boson case. So we will deal with Q equal 1. There is a vector representation. In quantum optics, this is typically called the lower level, the canonical basis of C2, and this is called upper level. So you can express the Pauli operators in terms of vectors. Remember that in our notation, when we have a vector in any pre-Hilbert space, and the element of Xi star is an element of the algebraic dual of the pre-Hilbert space, and if we write, this is the rank 1 operator, which to an element, say phi, in H associates the scalar, the vector, see it, rank 1 operator. Okay, so in these notations, Thank you. In these notations, the Pauli matrices can be written. These are the standard form of the Pauli matrices, and it is convenient to normalize them to take 1/2 for a commutation relation reason. And our operators sigma plus and sigma minus are expressed in terms of vectors as the rank 1 operators, which essentially flip the orthogonal basis vector. Okay? And important point is this, that we have already, these two relations are important because from them one deduces both commutation and anti-commutation relation. I think it's very important to emphasize that the commutation and anti-commutation relation are not, how to say, incompatible. The anti-commutation relation here are the standard anti-commutation that define fermions. And the commutation relation that you see here play another fundamental role in mathematics because they are the Lie algebra of the SO3, the simple orthogonal group. Orthogonal matrices with determinant +1. So the lower vector is annihilated by the S minus, and the upper vector, and it is S minus acting on the upper vector maps it into the lower one. Conversely, S plus rises the vector, so that is why they are called in physics rising and lowering. And you will see that in the central limit theorem, the intuition is that these are the Bernoulli analog of the creation and annihilation. And you will see that this intuition becomes a mathematical theorem in the limit. This is what I want to show in my talk today. Okay? That you have then these are mean zero, creation and the annihilation. Bernoulli creation and annihilation, like the boson 1, are mean zero. And of course, since they are nilpotent, this is identically zero. This is mean zero, corresponding to the fact that the lowest, the ground state, in the language of quantum optics, will correspond to the Fock state. And we will see that in the limit, this will correspond, this elementary property here will correspond to Fock. And this will correspond to more general, this is generally true, standard and norm. Now, we want to discuss and to describe the states on the 2x2 matrices. These states can be parametrized. It is interesting that there exists, these are a manifold, but they are a non-trivial manifold, because the states, let us say the pure states on the 2x2 matrices correspond to rays. So you have rays correspond to the unit sphere. And so you have two well-known parametrization of the unit sphere. The one which is based on the North Pole, and the other one that is based on the South Pole. So you parameterize the rays on in the C2, so these are unit vectors. And here the square root is an arbitrary complex square root, and Z is an arbitrary number inside the disk. And you will see that the elements of the disk, they are a complex number of modulus 1. And therefore, we will parameterize them by probability. And this gives the simplest mathematical content to the naive intuition that amplitudes are square roots of probability. If you look at the book of Feynman, he insists very much on this analogy. Okay? So we will use, in this parametrization, amplitudes are the complex numbers, and these are complex numbers are square root of, complex square roots of probabilities. And now we want to define the Bernoulli analog of the famous Weil operators. What are the Bernoulli analog of the Weil operators? Bernoulli analog of while operators are, you see, while operator is, I anticipate for future use, while in the, I have prepared some slides on the standard boson while operator, but just to fix your ideas, if you have the standard boson commutation relation, the while operator is are operators which are taken like this: Z bar A, Z A daga. These are usually, as you see, this is a skew adjoint operator. So if I multiply by I get a self-adjoint operator. Therefore, if this is a skew adjoint, this will be unitary. And these are the famous while operators. Okay? As you see, these are the, if I define now, this is skew adjoint. I multiply by I get a self-adjoint. And this is what is called the Bernoulli field operators. From the Bernoulli field operator, I will, exponentiating, define the analog of the Bernoulli analog of the while operators, or sometimes in physics called the spin while operators. Okay? Spin while operators, they have a nice, I have collected in this lemma, there are many interesting properties. Of course, you can say a lot. There is a nice book, I will also give you the reference if you want, entirely devoted to the analogy between spin and boson. But we want to make this analogy rigorous in the limit, so I collected the basic properties of the Bernoulli while operator. So, first of all, the field operator, the square is a scalar. This is a corollary of the anticommutation relation, but you simply do the calculation explicitly here, using the fact that S plus square is 0, S minus is 0, and then you have the anticommutation relation, and then what you have, this is what an interesting formula that we will very much use. So I will give you an outline of the proof in a short time. And as a corollary, you see, you have this unitary operator which maps this basis into a linear combination of these spaces. Okay? Pay attention that when Z, for example, is positive, you have just, if Z is positive, this part will be 1. But for us, most interesting case is when Z is, for example, purely imaginary or purely real. Okay? I will not enter in this because I have no time, but just, I mean, this square is very easy because, as I said, you do the product you use that sigma plus is square is 0, sigma minus square is 0, so only the cross will survive, and this will give minus z square. This is the standard formula. The skew adjointness is obvious. Just you take the adjoint, you remind that the adjoint of S plus is S minus, the adjoint of S minus is S plus. Now, let us come to the formula for the Bernoulli while operator. For Bernoulli while operator, you simply expand, and you take fz to the power, you simply expand, and you divide even and odd. Since there is I, the even part will give minus 1 to the power case, and also this. But here there is plus 1. So I will bring 1 outside. So I reproduce only the even. This is a very standard trick and very useful to, for example, in the theory of dynamical system. When you replace this to any operator, you can make this trick for any operator, and you get the solution of any linear Hamiltonian system. It's exactly this, the idea. Okay, so you see, in the 2x2 case, if you go deeply to the 2x2 case, you will discover a huge quantity of properties that are true in general. So, what is this? This is the cosinus series. And this is the sinus series. See? But I need an additional power. That is why I divide here and not here. Here I have all the powers I need. But here, this is an error. This plus 1 I could put because I put the denominator. Okay? Otherwise, I would have left 1 to form the sinus. So we have the while operator. Please remember this formula, which will be important. That the while operator is just this one, the Bernoulli while operator. Now, a quick remind about the usual boson algebra. You have that standard Heisenberg algebra was for P and Q. But given P and Q, you define creators and annihilators. It's a one-to-one, and in fact, the square root of 2 is put because in such a way, the relation between the two is given by a unitary matrix, okay? So, if you have from the commutation relation, just by taking derivative in T, you find that this is the unique solution, and that P acts as a translation of Q. This is a well-known fact, but I didn't give the proof. So if you take powers of this and powers of both sides, and you use the and then you do the exponential series, this will converge on analytic vectors. Then from this side you have EIP, EISQ, and from this side you obtain nothing but EISQ. I multiply by IS both sides, and then I take the exponential series. This has been cut off, but you get the famous while relations. Okay? The while relations that will play an important role. Now, we want to use the while relations, but not for P and Q. We will use for A and A daga. And so, what we do, we use a very well-known result in quantum mechanics, that if I have two operators that commute with the commutator, so A commutes with the commutator of AB, and B commutes with the commutator of AB, then the product of the exponential is expressed in terms of the exponential of the sum. This is a useful property, and let us apply to the particular case in which A is minus Z A daga, and B is Z bar A. So this gives you the scalar which commutes with everything. And of course, it commutes with the commutator. Therefore, I apply this formula. And this is called, in physics, is usually called the disentangling theorem, because it takes an operator of this form. Pay attention, here I have on the right the annihilator and on the left the creator. This is what is called normal order. Whenever you have an expression and you put all annihilators on the left and all creators on the right, you call it A daga normal order. People say simply normal order, but the normal order, of course, normal order for P and Q is different from normal order from A daga. So when the normal order is something that strongly depends on the basis. This normal order is very important because it gives a way to compute. It shows that this is the famous rule of quantum probability. Algebra implies statistics. So this is an algebraic formula. This disentanglement is an algebraic formula. Take expectation value. Use disentanglement. But since A phi is equal to 0, the exponential of A applied to phi will be fixed. This is well known. Exponential leaves the vacuum fixed. And therefore only the scalar term survives. This is Gaussianity. So, what is a Gaussian state? A Gaussian state defined in terms of while relation. A Gaussian state on the from the while relations, I give it, we are in one dimension. So here the scalar product is simply the u bar times v. We are in one dimension here. This is the Weil relation that we will use. Now, what happens? From this relation, you see that the linear span of the Weil operator is a linear vector space. But due to this relation is an algebra. It is a rather deep theorem, non-trivial, that there is a unique C-star norm on this algebra. Okay? So you can close this algebra. This is algebra without any, it's a purely algebraic relation. But there is a unique C-star norm up to isomorphism, and you can close it. And this is called the Weil C-star algebra. You can work also with the Weil star algebra. What is important is that you call a Gaussian state. You will see there are many very beautiful lectures by Partasarati, who recently wrote on Gaussian state on the boson algebra. So I suggest you strongly to read his paper, which is very, very expository and systematic. I am doing only the extremely elementary part with 1 degree of freedom. So I say that I take the Weil algebra over the complex numbers, and this is maybe interesting for you. Take any state on the Weil algebra, because this is a general. On the Weil algebra, this can be complex or real or it can be any Hilbert space. This is not so important. You will use this commutation relation. So the state, we say that there is a unique C-star norm. So we can speak of states that they have good properties. So if I have a state, I know that any linear combination must be positive. So this must be positive. That means that I have well, there is another important relation. I didn't write, but this is clear. These are unitary operator, and the inverse is this one. So I will put directly minus zj here, and w z k a k. The a are complex numbers, okay? Now you use the Weil relations, and you get that this is equal to sum aj bar, and you bring it out the e minus, this is plus because there is minus here, and zeta I imaginary part, scalar product zj zk, and now you have here w of zk minus zj, and here you can take expectation, and here you put aj bar ak. So, you see, this is a kernel. This kernel is important because it is positive definite. And the converse is true. But it's positive definite, pay attention, not in the standard probabilistic language. Because in the standard probabilistic language, you call a kernel positive definite, but this is absent. Okay? The positive definite kernel on Weil algebra is not what is called positive definite in standard probability theory because of non-commutativity. And the theorem is that there is a one-to-one correspondence between positive definite kernel in the boson sense on the Weil algebra and the linear functionals. You can check that this prescription, the quadratic prescription, is positive definite in this sense. So it describes a Gaussian state. Such states are called Gaussian. So Gaussian states are those. What is the logic? Any state on the Weil algebra is uniquely determined by what we have proved here. I mean, I stated the theorem, did not prove. That a state is equivalent to a functional f of z, which is positive definite in the bosonic sense. Okay? And now, as an example, we take fz equal E minus 1/2 mod z squared. Okay. So let us go and see the... Okay. So the while operator, I already wrote on the blackboard, are like this. So you see that the while operator, boson while operator, are exactly the quantum analog of what we called the Bernoulli while operators. And these are the while relations we already discussed. Okay, I don't go into this, is not so important. Field operator are introduced also in boson case. Okay, you see? Of course, while the field operators in Bernoulli case, which are the Fermi field operators, are bounded because their square is equal to a constant, the boson operator are unbounded. Boson Fermi field are unbounded. Okay? And we have these commutation relations, which gives the symplectic form given by the imaginary part of the scalar product. In particular, you see the momentum will correspond to real valued element of the fields are parameterized by complex numbers. Those by the real line are momentum and imaginary line are position. Now we come to the basic ingredient of central limit theorem. In central limit theorem, you have two fundamental ingredients. One is independence. The other one is embedding. In the von Waldefels lemma, we did not speak of embeddings. Now we begin to speak. And we consider the most famous and the most, in some sense, most important embedding, which is the tensor embedding. The tensor embedding simply means that I have a set V. Remember, V means vertices of a graph. And I have, these are algebraic generators, not only linear, non-linear, but algebraic. Because when you multiply them, you obtain n plus n minus, the projection, and they form a basis. So, if you want, not all embeddings are homomorphic. There will be, for example, some Q-deformed embeddings will not be algebra homomorphic, but they will be vector space homomorphism. And they are good enough to prove the central limit theorem. What do you mean?
Vector space, only the level linear.
Only the level of linear space. They will not be star algebra. Another important class of non-star algebra homomorphism.
Property is not needed for central limit theorem.
Not essential. Not essentially needed. Another important property that has been used in the literature is a Lie algebra homomorphism. And they correspond to different notions of stochastic processes, you see. Because the stochastic, roughly speaking, the intuition is the same that you have from Lie algebra and Lie group. The Lie algebra description of stochastic process, roughly speaking, corresponds to stochastic differential equation. And the group description of stochastic process corresponds to group representations, okay, to solutions of these equations. Now, we take the very simple embedding, which is so-called tensor embedding, and the tensor embedding is essentially characterized by this property. I take an arbitrary vector, an arbitrary 2x2 matrix, and I associate the element of the infinite tensor product, which on the nth factor is equal to x, and everywhere else is equal to the identity. NC means the set theoretical complement. So I have identity on the set theoretical complement. Okay. And now recall the one-dimensional while operator. The Bernoulli while operators were defined like this. Now we want to go to the n copies of the Bernoulli, and so we define the while operator as the product. For simplicity, here I took the same z, but of course you understand I can take different z on different factors, and we will use this in the central limit theorem. Okay? Now, look what is important of this embedding. The fundamental property of the tensor embedding is the commutativity. And this, if you remember, when we dealt with the general central limit theorem, we arrived to the entangled ergodic theorem, which was equivalent. But when you have a commutativity of this means commutativity means GHX GKY is identically 0 for all H different from K, and from all XY belonging to the 2 by 2 matrix. Okay. Now this means, as you see, when you have this, there is no entangled ergodic theorem because everything commutes. So everything is reduced. You don't need any condition. So we could deduce immediately the central limit from von Waldenfels lemma. But I want to follow in this talk a completely different route. Why? Because I want to show that when you have additional structure, you can, as it was done in the history of the first central limit theorem were proved by direct calculations. The singleton and strict singleton condition appeared much later. So let me show why the situation is very simple in this case. You do some estimate, but so look, you have an exponent. Since you have a tensor product of exponentials, and they will be rescaled in this way at the moment. Forget the rescaling. I don't introduce at the moment the central limit rescaling. But this is for arbitrary z. Since they commute on different factors, the exponential of a sum is the product of exponential is the exponential of the sum. So I have this. Remember Sn, my notations, I wrote in the transparent, but I want you to remember. In my notation, when I write Jnx, I also write by definition xn, and this means that there is 1 everywhere in the complement of C, and there is x in C. Okay, now you have this sum. So you see that just by taking tensor product of Bernoulli while operator, you are immediately led to work with the z rescaled like this. You are immediately led to consider central limit theorem. But now you see, in the case of when you take expectation of this, you get analytically a stronger result. Why? Because when we did the central limit theorem, we proved the moment central limit theorem. But this, remember, Zs minus Z bar S minus is skew adjoint. So this exponential is the exponential of a skew adjoint operator. So it is a characteristic function in the probabilistic language. So now, for while operator, we can have a better, from analytical point of view, central limit theorem, because we deal with the characteristic function, not with moments. So these are there is equal that has bin forgotten here. So I therefore, motivated by the product of while operator, I introduce the central limit sums, which are this. There should be equal here and equal here. Okay? I have three fundamental operators. As you guess, this operator will tend to creation and annihilation. What will be the limit of this? You see, and there you will, and I think I will explain in the future lectures because it's a subtle point. It depends on the state. It may be the number operator, the identity, or 0, according to the states. Now we will particularize. We are in a very particular context, but I will further particularize. Remember, we had a general singleton states. Now I take a tensor product state. You understand what is a tensor product state if you write the definition of tensor product state on this algebra is just, remember that I have the embeddings, J, from the 2x2 matrix into the tensor product of V copies of the 2x2 matrix, and by definition a state is called the product state if whenever I have this product of Jk, K is a finite set, K belongs to a finite set of xk, you see, this is well defined because everything commutes. Now I don't need to take the order, and this will be the product of the expectation. So this is exactly as we have in classical probability. By the way, in this case, the tensor case is really almost commutative, but what is J in classical probability? Well, you have a classical, I think I already said, but if you have a sequence of random variable, or in general an arbitrary set of random variables on a probability space, and with values in an arbitrary measurable space, you, for any function f on belonging, this is a measurable space, so it makes sense to speak of the measurable functions with complex values on this space, okay? Bounded measurable function. And this J, T, will be the homomorphism, which takes a bounded measurable function on the state space and brings to Jt of f, which by definition will be equal to f composed with ft, with xt. And this will be a bounded measurable function now on the probability space. This is the good analog of random variable, because you see, this homomorphism always exists. But many people say the quantum analog of a random variable is an element of an algebra. But if the algebra is a state, to say that this is an element of the algebra implies that all powers of xt are in the domain of phi. And this implies that all moments exist. But we know many random variables have no moment. And this notion of random variable takes care of this limitation. This can be true for all random. You don't need moments for this definition. Okay? So that is the J embedding. And now you have the definition of product state. In particular, I can define the definition of always in analogy with probability theory, the distribution of the random variable J is, in this case, will be P composed with J, T, and here is the state composed with J, T. This will be the marginal distribution of the random variable xt. If this is equal to phi of some fixed point of v for all t, well, the index set we called V, for all t, then we say that the state is homogeneous. That is, all marginals are equal. Therefore, an homogeneous product state is a product state which, on any finite set, is an homogeneous product of copies of the state E0 on the single 2x2 matrices. So we are reducing everything to 2x2 matrices. For example, take the state 0, 1, the ground state for the spin system, and take its tensor product. Take expectation with respect to this state, and you obtain a product state. This will be, we will see in a moment, is the analog of the Fock state. Now I give you my main theorem. So you remember that the essence of Gaussianity was quadratic form. Okay? And if you, what is the intuition about Gaussianity? Take the what is the fundamental point? Remember, the Weil algebra is the linear span of this. Take now, but in finite dimension, we have not such relations. So the finite dimensional, the Bernoulli Weil algebra, is not the linear span of this. Okay? It's the algebraic span. I need the products. I can't, because such a simple relation is only in the limit, not at the Bernoulli level. So I need, if I need the approximate Bernoulli, I will need to consider products of them. What I want to prove? I want to prove that for each k, this expectation value, n, remember n is my homogeneous product state, will converge. First of all, first part of central limit theorem, this will be convergence in distribution. Second, we want to explicitly individuate the limit. And the limit, you see, is a quadratic form. This is a constant because these are two constants. Because if you have a state, suppose you have a state on this algebra, you have the algebra M2. And we say that S plus and S minus are algebraic generator. So their product generates everything. Suppose that I take a state with as a mean 0. Then what will be the covariance? The covariance will be a matrix. Because remember, I have the quantum observables are analog of vector observables. In this case, I need 2 because I want a self-adjoint set. So the covariance will be E S plus, E 0. I put 0 when I take only two-dimensional object. E0, S plus, sorry, let me write like this. S plus, S minus. S plus, and S minus, and S minus, S plus. So this is the anti-Fock term. This is the Fock term. And these are the so-called the terms of diagonal. A state on the 2x2 matrix algebra will be called gauge invariant if the off-diagonal terms are 0 of the covariant. Gauge invariant because it means the expectation value, the covariance, is invariant under the gauge transformation. S plus minus goes into EI alpha S plus minus. The same alpha, pay attention. Well, in fact, it will be plus minus alpha. Okay, they must be always adjoint of each other. Okay?
Your state may not be invariant under the gauge.
Huh?
Your state may not be invariant under the gauge. You're just taking the translation. You're taking a very specific state, right?
Very specific, which is also translation. Well, I have an abstract lattice, so I have abstract graph, so I don't need to have translations.
How can you guess that this actually
How do you get the covariance set? You will see. This is the proof. You will see. So the covariance of the these we proved that.
Some condition is needed. So your state is.
But we have a huge condition, enormously strong, which is the product.
But this is not true for any state. You choose.
No, not true, not true.
So there is some secret.
Of course, well, not secret. We are now in this very strong, simple example of product states.
Yeah, it's very
Asymptotic, but the fact that the states depends on the covariance is very general.
Yeah, that I understand. But
It's very general because we proved in the central. If you remember,
you can classify all the states that you can that will have the gauge invariant term. Classify all the translation invariant state. Only central limit theorem will be true.
I can.
Classify them all.
I can classify in the following sense that if I start with a gauge invariant state, the limit will be gauge invariant.
That is like okay. I agree.
But the other way around, what does it mean classify? This is a definition. A state is called gauge invariant, and the boson state, of course, you replace the boson operator, and you get gauge invariant. So it's a definition of gauge invariance. You see, it's not a matter of definition. You must classify the diagonal matrix.
I put in the while operator I put a phase. I put e to the power I theta in Z1, Z2, Zk. Let's say.
Right.
I theta.
No. In ZK,
I
this
see if that
No.
limit is independent of the theta.
no.
Then I say my
No.
theta is independent of the theta.
The gauge transformation is not acting on the Z. It's acting here on the generators.
So this see the right hand side that you wrote down here, it is actually invariant under the gauge transformation.
The gauge transformation for generator.
My question is, what are the states for which you will have a covariance term, or this is a general function Z1, Z2, Zk, that will be invariant under the gauge transformation. That is Z1 goes to e to the power I theta Z1. So because this is related to, you understand, there's a 2-point correlation function and n-point correlation.
Exactly. This is a.
Then I can say all this you don't need to compute all k correlation.
We are
You
assuming.
have to compute 2 correlations.
Right, we are assuming, you see, in our case, the correlation is trivial.
Yes.
Because in our case, we are assuming the fundamental assumption is that we have that En is a product state.
Yeah, this is very speculative.
So, of E0. So, if I have the correlation, the 2-point correlation function, JH, X, JY, JK, Y, and H is different from K, this is simply E. Because of stationarity, this is not only a product state, but it corresponds to identically distributed random variable. So tensor product means independent. Homogeneity means identically distributed. Okay? So since they are identically distributed, this will be E0x, E0y. So for these states, pair correlation are trivial. Of course, when you take non-product state, you will need.
In fact, Leo's central limit theorem is true for any translation invariant state, which is deflection positive.
Well, you speak translation value because you are thinking of lattice.
No, yeah.
But I am a graph, so I speak homogeneous because what is translation on a graph?
Put it in a graph.
Right.
Graph.
Yeah, homogeneous state.
Yeah, homogeneous.
So this is the simplest possible. That is why the Moivre Laplace. Because historically, this was the first central limit here, even for 2x2 case. And I am doing the quantum analog of the De Moivre Laplace, which is the spin 1/2, 2x2 matrices. Okay? Now, you see that you have this product. This product you can reduce to a single one up to a multiple. Because we are in the boson, we want to prove that in the limit we get a Weil algebra. But not in the discrete case, not in the approximation. You see? Because I explained this point. These relations are true only for the boson algebra, not for the Bernoulli algebra. So this product does not reduce to a single one in the Bernoulli algebra. In the boson it does, up to a multiple. But in the Bernoulli not, you have to take care. But
in the limit you get right.
you will, now I show you what is essential for the limit. And this is my main point I want to arrive, is the order of magnitude. You see, you must, that is what is easy to understand here, because computations are easy, but they give you the correct hint for order of magnitude. And you will see that the non-zero mean term must be expanded to second order, and the zero mean term is sufficient to first order. You will see why. So, we want to prove this. And now you recognize the quadratic expression that comes this. If you have why this expression is boson, is exactly what would come from boson. Take the case of limit. So imagine that you are now n in the limit, and imagine that this is the boson algebra. Okay? Then you apply the while relation iteratedly. So you couple 1 and 2, and then you get E minus I imaginary part of Z1, Z1, Z2. And then you have E of W, Z1 plus Z2, and then you begin with Z3 and go on. And now you apply the same with this. And you get, you see, iteratedly, you will get another factor. Now you have Z1, Z2 with Z3. Eventually, you will multiply all. What you will get? E minus I, imaginary part, or if you want to sum, of the imaginary part of all the products for j less than k of z, j, zk. And the last, what you obtain, every time you add 1. So in the last you have sum z1 plus z2 plus zk. And here you apply Gaussianity. This is the square. And then you apply a simple algebraic identity that I will show you. So if the limit of these objects, so you start from objects which have not this boson property, which is En and Wn, Z1, W1, Z1, Wn, Zk. Z1, Zk. Okay. And you want to prove that this object converges to this. And if this is the boson, what I expect, it should have this form. And this should be the expectation of the while operator on the sum of all these objects. If the state is Gaussian, it must be a quadratic expression in this. And you see, this is also quadratic. Okay? Now, why quadratic expression comes out? This is from, so this is Gaussian state with this covariance. From where it comes? So, you start with this sum. Remember, each while operator is a tensor product of capital N copies of the same. So this is Z1, and this capital N copies of this. So, when I compute this, I am using, here I did the two-step in one. One, I take the product of all homogeneous terms. They are all equal. So on each component of the tensor product, I have the same product, which is this one. But I have n components. And I have a product state. And the product states are all equal. So I have this to the power n. Is clear this step or not? Or you want me to explain in the blackboard? Well, it is easy.
We did it in our master's program.
Huh?
When we were graduate student, before we were graduate student in ISI, this question in the exam.
This is the example.
Yeah. In
This
the
is
exam, you put this.
exam. I thought the example.
No, he gave this question in the exam.
No, this is what I said is simply this. I have En of Wn. Let me do it with the 2. K is equal to 2. So you will understand Z1, Wn, Z2. Okay. So this is equal to En of W Z1, W0 Z1 to the tensor power n, and this is W0 Z2 to the tensor power n. It means on each point of this set I put a WZ with the same Z2. This means that I have En of what? W0 Z1 times W0 Z2, everything tensor power, this is n. But now I use the assumption that En is a product state. And by definition, expectation of a product is product of expectation. So this will be, but the operators are all equal. So the product of expectation is a power. And this is the cardinality of the set n. So this will be E0 of the single. Remember, for each of these, we are in M2, the 2 by 2 matrices. While these objects are M2 to the tensor power n. Okay? So I use that this is a product state, and this will be E0 of W0 Z1, W0 Z2, everything to the power n, because they are all equal, homogeneity. Okay? And this I am doing for k instead rather than for 2. Now, remember that each operator has this very special form. However, I have not z, but z renormalized. And so I wrote explicitly to show that whenever there is the quotient, the normalization cancels. Only the phase remains. I am doing a particular case in which the phase doesn't depend on n. There are central limit theorem also in which you can take phase and randomize phase. They are more complex. But I wanted you to have the basic order of magnitude. So I am dealing with the simplest possible situation. So this is the final expression for a single W0. But I have a product of them. So I must calculate a product of this W0. And therefore I have a product of cosinus plus these terms. Now, cosinus, you expand, and here is the point. Cosinus you expand to second order. Because you remember, you have this power n. So you use the fact that 1 plus x divided by n to power n will converge to exponential. Okay? So I need something of order n. So what does it mean? That the cosinus, I have to expand at least at order n, because I have 1 plus, let me write it down here. I have something, comes from cosinus, and this is the order 1 over n squared that I will, in the limit, I will neglect, because there is the power n. Then, now, however, I have also a term of square root of n, which is smaller. So I have to keep all the terms of square root of n. See, when I have these products, the 1 will give me 1. The terms of order n, for each of them, 1 will survive, because any other one will be multiplied by other powers, quotiented with them, will be higher order. So only 1 survive, and I will have the sum. Similarly, the term here will survive, But you see, here, when I take the product, since it is square root of n, I must take the product of 2. And you begin to see the covariance building up. Okay? Now, I have, and whatever remains now will be of order 3 over 2. Because this will give me order n square, and this will give me order, the first power of sinus is 3, because sinus is odd. There is square root, therefore I have 3 over 2. Okay? So this is, I think, the most important from the point of view of intuition of order of magnitudes going on. And now everything will be easy, because you see, you have only to calculate, because you have that this expression, see, this is an operator, because there are s plus s minus. But whatever the operator, it is bounded. Even in norm is bounded. I don't need to take expectation. This is important. First central limit theorem were done for expectation, but you can have a much stronger in 2x2 case, in this Bernoulli case. Okay, so let us come up. What we have? We have this term. And then we have to take E0 expectation. You see, I have this product, and I have expanded this product up to second order or first or mixed expansion, and I have to take E0 expectation, and then to take the power. So the E0 expectation gives me the covariance, because you see, here I have this product, and here gauge invariance is automatic. Gauge invariance is automatic, because if you remember, the operators are nilpotent. The operator s plus minus square is 0. So, by definition, you have gauge invariance with such operators. Okay? So you have this product, you do this product, and only the term plus minus and minus plus survive. Notice that plus will go with conjugate, and here the j will be with conjugate. So they exchange the conjugate. Eventually, I obtain the taking E0 expectation, the covariance will appear. This covariance. So I have the covariance here, and something negligible. And therefore, I have this limit. This is true for every dimension, not necessarily 2x2. You can have even infinite dimension. Of course, you need to put some more. For infinite dimension, you have to put some more. You don't need stationarity or homogeneity. You don't need product states. You need simply decay of correlations. You need. These cases are increasing difficulties. Yeah. In fact, in the literature, there is very little. There is only the first paper. The first quantum, right, the first quantum central limit theorem was done by Bach and myself in 70, roughly speaking, I think it was 73, 74. No, I don't remember, 77. And then Ferber took, and we considered only mathematical aspect. Then we did a long paper with Lou, with more complicated commutation relation, and non-product states. But the literature on non-product states is not so wide. I have seen that in the past years, not so, but in the past years, some physicists began, or mathematical physicists began again to take this line initiated by this paper by Bach and myself. Okay, so now you have this. I think we have to finish, or I will show the Fock the other time. The Fock case is simpler, because this term will be vanish, and then you apply a simple identity, and you see very evidently the commutation relation.
You will also derive fermionic case also? Give some example.
Yes, Fermi, the central limit for Fermi, there is.
It will be it's more complicated, right?
Yes. This generalization of this construction for Fermi was done by Lou. because he was my student and I suggested this problem, to do this in the Fermi case, and this was the beginning. Then, many, many years after, we introduced the interacting Fock space, and that was the idea. Look, the boson Fock comes from Bernoulli in this way. The Fermi, Lou had proved, it comes in analogous way, but more complicated combinatorially. What about interacting Fock? Lou worked on this, and he produced what now is called the monotone independent.
Can you get this implemented for fermionic type
Yes.
from this spin chain?
Yes. No, not from tensor.
From the spin, from
No,
the tensor
it's not spin chain.
No,
They must be anti-commuting.
No, so yeah, but some other kind of embedding, not this kind of
No, this is tensor.
So you have to do fermionic
Right.
embedding.
Right, fermionic exactly.
Then the central limit theorem will give you fermionic.
Exactly. This is the Lou theorem. But the Lou theorem is rather complicated combinatorially. This is easy, and the order of magnitudes are very easily understood. Then you have a combinatorics. You see, combinatorics can be complicated. See? Okay, next time I will try to show.
CR algebra, it will give you the fermionic central limit theorem.
Huh?
If you embed it in a CR way,
Exactly.
then it will give you the fermionic.
Exactly, but this was already done. In fact, the first fermionic theorem was done by von Waldenfels. Yes, before Lou.
But Bernoulli school doesn't talk about fermionic case.
No,
They only talk about only
no,
boson.
the only boson. But von Waldenfels already did the first Fermi central limit theorem. What we did with Lou, you see, what I want to show in the future lectures is that, you see, in the classical probability case, you have only one measure, and you always work with it. In the quantum case, you have a correspondence between measures and states. And on the boson algebra, you have a lot of physically interesting states. There is the Gibbs state, there are the number states, there are the exponential states, and you can see how to build all this structure from Bernoulli. That was our idea to approximate the Gaussian, the quantum Gaussian with quantum Bernoulli. Quantum Gaussian is enormously more rich than classical Gaussian. See? Because you have the Gaussian is the representation, but the states are many, and so you have many. For example, photon statistics is a point statistics, it's Poisson. So in the Gaussian statistics, you have also the Poisson limit theorem. This is the point. In classical Gaussian, you have not Poisson; they are separated. In classical Gaussian, there is everything. Okay.
In the previous slide, there was a term by 1 by square root n. For calculating the Sharp quantity, there was a term by 1 by square root n. But how did that disappear?
Because this is the second order. This is the product.
Yeah.
You see, when you have a, let me explain. This is very interesting. When you have this product of k terms, you imagine each of these is a quantum characteristic function. E to I is a self-adjoint operator. This self-adjoint operator, because of the normalization, is of order square root of n. When you write the Taylor expansion, see, because of this square root of n, you must stop to the second order. And when you have this product, only the product of 2 will give 1 over n. All the other ones will give a higher power, greater or equal than n to 1/3. That is why that disappears.